All right, guys, so we're coming closer to the middle of the chapter. There's one topic that we really want to start discussing, and that is the topic of what we call source transformations. Now, remember what we talked about when it came to equivalent circuits. Whenever we have two circuits that have a single port, the two circuits are said to be equivalent circuits if for every voltage you place across the two circuits, you draw exactly the same amount of current for every single possible value of the voltage in the current. Now, the reason the concept of equivalent circuits is important is because if we find two circuits that happen to be equivalent to one another, anytime we see circuit number 1, we can replace it with circuit number 2, and anytime we see circuit number 2, we can replace it with circuit number 1. This led us, mathematically, to be able to define what it meant for resistors to be in series, for what it meant for resistors to be in parallel, and Y to delta transformations, Y to delta transformations, and things like that. So it is a very mathematically and physically fruitful idea, this concept of equivalent circuits. Now, one thing that we have not discussed, however, is are there any circuits that are equivalent circuits that contain either voltage or current sources? And it turns out that there are equivalent circuits that contain these types of sources. And that's what this is about, the concept of source transformations. Now, one thing that I really want to make mention of as well, and I'm just going to verbally mention it right now, is that the analysis that I'm going to do right now is different than that which can be found in the textbook. I want you guys to be able to approach problems using multiple approaches, knowing that it's going to lead to the same results, right? So just wanted to let you guys know that the approach in the textbook, absolutely perfectly valid. However, I'm going to derive the same things using a different set of concepts. Now, to start with equivalent circuits, we really do want to start with the two circuits. And so we have some black boxes here that are going to constitute our circuits. And this circuit number 1 here has a port, 2 terminals. And circuit number 2, similarly, we're going to place into our black box, and later on we will open it so that you know what's actually in there. And again, it has 2 terminals like this. Now, suppose that I go to circuit number 1 and I take off the lid, and one of the things that I find is I find a resistor here in series. Whoops. Let's go ahead and correct that. I find a resistor here that happens to be in series with a voltage source. And the voltage source has this particular polarity. I'm going to call the value of this voltage source Vs and the value of this resistor Rs. Right? So the key thing is we have a voltage source in series with a resistor. And then I go to the second black box, and one of the things that I do is I open it up. And in the second black box, what I find is I do find another source, except this time it happens to be a current source. On top of that, there is a resistor in the circuit. However, it happens to be in parallel with the current source. Right. So here I'm going to call this resistor Rp, and I'm going to call this current source I sub P. So notice that I've chosen subscripts here to remind you of what happens to be in series and what happens to be in parallel. Right. Now, in general, and this is really critical, in general, these two circuits for arbitrary values of Vs, Rs, Ip, and Rp, they are different circuits. You cannot replace one with the other. However, under 2 special conditions, you can actually force these two circuits to be equivalent circuits in such a way that anytime I see circuit number 1, I can replace it with circuit number 2, or anytime I happen to see circuit number 2, I can actually replace it with circuit number 1. This is what it means for these circuits to be equivalent. Now let's go ahead and mathematically write down some equations so that we can figure out what the relationships must be between the elements in circuit 1 and circuit number 2 so that they are equivalent circuits. And I'm going to start off the way I usually do, and it's going to be to externally place a voltage across these two terminals. Every time I place a voltage across those two terminals, I'm going to draw a current I, like so. And notice that for the circuit, I can actually define a loop here, a very clear loop, like so. And I'll call this loop number 1. And I'm going to use KVL around that loop to write down an equation. Now, very clearly, this current I itself, as it's going through, it is going to go through the resistor R sub S, like so. That means that there is going to be a voltage across that resistor that has this particular polarity. I'll call this V sub S, and V sub S is related to the current I in the resistance RS through Ohm's law like this. Now I have everything that I need in order to write down KVL. So KVL around loop number 1, what I'm going to do is I'm going to add up all the voltages around this loop, and they must add up to 0. And I'm going to go in the direction as specified by my loop. So the first one is I'm going to start going around my loop, start over here, and then I'm going to start going in that direction. So the first voltage that I encounter in KVL is the voltage across my resistor. Notice that I hit the positive sign first, so into KVL goes the voltage V sub S, but that is plus I times R sub S. I then go through my voltage source V sub S, and I hit the positive sign first, so I have plus V sub S. And then I go through my external voltage, this voltage over here, and notice that in my loop I'm hitting the negative sign first. So here I end up with minus V, and that happens to be equal to 0. One thing that I'm going to do is I'm going to rearrange this equation a little bit. I can multiply everything through by a minus sign, and I can rewrite this equation as V minus I R sub S minus V sub S. That's equal to 0. This is an important enough equation to name. This is my equation number 1. Right. Now, for circuit number 2, I'm going to undergo a similar analysis. Now, again, since I want these two circuits to be equivalent circuits, every time I place a voltage across the terminals of circuit number 1, I must be placing the same voltage across the terminals of circuit number 2. So here I'm going to place a voltage with this polarity, and it has the same value as the voltage for the first circuit, and if they're going to be equivalent, then that current I must be identical for both as well. Now, over here I do need to define some variables. Right? Notice that for the resistor R sub P, I don't know anything about that voltage, I don't know anything about that current, so I am going to go ahead and define, a current flowing through that resistor, and I'm going to say that that current itself is going to go down this way. And I'm going to say that this is a current I sub R like this. Right? Now notice that in the circuit at the very top here, I have one really large node, node A, and I can actually, since I know the currents flowing through each one of those elements, I can actually use KCL at that node. Right? So here, for the circuit, I'm going to use KCL at the node A that I just defined. And the version of KCL that I'm going to use is the sum of the currents that are flowing into this node has to equal the sum of the currents that are flowing out of this node. So this is at node A. Now, into this node, we have actually two currents. We have I sub P, this current, and we also have this external current I. So on the left-hand side of the equation, I have I sub P minus I plus I, and on the opposite side of the equation, it is only I sub R here that happens to be flowing out of this node. Therefore, this is I sub R like this. Right. One of the things that I can do is I can use Ohm's law to write down some equations here as well. And I can also isolate this I here, right, by rewriting this as I is equal to I sub R minus I sub P. And this I sub R should also be related to the voltage V across it. Notice that this V that's external, well, that is the same voltage that's applied across that resistor, RP. Why? Because they have the same nodes. So one of the things that I can do immediately is I can say that this voltage is the same as that external voltage, and Ohm's law tells me that for that resistor, V is equal to plus I sub R times R sub P or solving for I sub R, I get that this is V over R sub P. Now, this equation I can actually substitute into there like this, in which case I get that I is equal to V over R sub P minus I sub P. This equation is important enough to number as well. This is going to be my equation 2. Right? Now, notice that these two equations, equation number 1 and equation number 2, they apply to separate circuits. They're not the same circuit. Equation 1 only applies to circuit number 1. Equation number 2 only applies to circuit number 2. However, since we are forcing these two circuits to be equivalent circuits, the I's, V's in equation number 1 and equation number 2, since they are equivalent circuits, they're the same values, they're the same variables. Right? So here, by equivalent circuits, we can use 2 in 1 and just literally directly plug it in. Right? So over here, what I'm doing is I'm taking this equation, plugging it into there, and I am eliminating the variable I. So by doing that, the equation that I'm left with is V minus, well, I, which is V over R sub P, minus I sub P times R sub S, minus V sub S, that's equal to 0. And one of the things that I'm going to do is I'm going to gather all of the terms that have V together. So this term has V, that term has V. Notice that I have to distribute that. The other terms do not, so I'm going to group those together. And I can rewrite this equation as V minus RS divided by RP times V. So that's from this term times that. And then I have minus times minus gives me plus. I have plus I sub P times R sub S minus V sub S, and that's equal to 0. I can then factor out from here and there the V's, and the equation that I'm left with is 1 minus R sub S divided by R sub P times V. And then I'm just going to place a parentheses around the rest. So I have parentheses I sub p r sub s minus v sub s, and this is equal to 0. Now, this is the key step. This is the major step, right? This is one of the reasons why I'm starring it. This equation that we have here, and let me box it as well. For what values must this equation work? If the two circuits are going to be absolutely equivalent circuits, this equation must work, be true. And this is the key for all possible values of V and I. So the V and I that I'm talking about are this V and this I. That equation must work for every single last one of them. Now, if V is kept as a variable, this equation is constant times variable plus constant, and that is equal to 0. So this has the mathematical form of constant times variable plus constant, and that's equal to 0. Now, from algebra, one of the things that we should have learned is the solution to this has one solution, x is equal to b minus b over a. But that's one single solution. So the only way that this equation can be true, and this equation can be true for every single last possible value of x, is this is only true for all possible values of x here, if and only if a is 0 and b is 0. So if a and b just happen to magically be 0, then I do not care what I plug in for x. That equation is going to be true for every single possible value of x. So the requirement for these two circuits up here to be equivalent circuits, we have two requirements. The first is that 1 minus Rs divided by Rp is 0. That's the equivalent to saying A is 0. Or notice that this is the same way of saying that Rs is equal to Rp. And since they're going to be equal, I can just define that as a single variable R. So that's the first requirement. And the second is there's a relationship between the voltage source in the first circuit, the current source in the second circuit. It kind of looks like Ohm's law. It's that I sub P times R sub S minus V sub S equals 0. Or using the first result, equation number 1, it is that V sub S is equal to I sub P times R. So this is important enough to box. This is important enough to box. Notice again, this looks like Ohm's law, that second equation. It is not Ohm's law. It is not Ohm's law because V sub S and I sub P refer to completely separate circuits. Right? They are both sources in circuit number 1 and in circuit number 2. But if these two things are true, right, then anytime I happen to see a voltage source that happens to be in series with a resistor, I can then replace it with a current source that happens to be in parallel with a resistor like this. These two circuits are absolutely equivalent, so anytime I see one, I can replace it with the other, and I can do that to simplify my circuits. Now, one thing that I really want to make mention of, and this is kind of a warning, when it comes to the voltage polarity and the current direction for the two circuits, you really happen to have to pay attention. One thing that is exceedingly important is notice that the voltage polarity here is such that the top is positive, bottom is negative, and the current direction must also be respected. Notice that that current direction goes from the negative terminal of the voltage source up to the positive. It is not a proper source transformation if the current direction and the voltage polarity for both of these is not respected. This is enough theory. We will get a chance to use these source transformations in later videos so that you can actually gain some practice using these in order to help you simplify circuits so that you can solve them. Thank you very much.